Okay, did you have a look at these homework problems I sent you?
I never received your email.
Okay. Let me verify that I have your email address. I got AIZA01 at...
No, it should be AIZAKS01.
Let me change that. AIZAKS01 at Gmail. Okay, well, then I suppose one good thing we could do tonight is to look at some of these. Go on, but we'll see how good. I'm not sure we've covered all of these, so some of these might be actually a little tricky for you. Let's just go through each one of them. It's 4 times 16. So how am I going to do this problem?
First you have to do parentheses.
Okay, tell me what this is, how you're going to break this down and come up with a number.
Well, you could also do log base 4, or log base 2 4 plus log base 2 16.
Okay, so that's a good first step. Log base 2 of 4 plus log base 2 of 16. And then what number is that?
Would it just be 2?
Uh-huh. And what number is that?
4.
Correct. So the answer is 6. Notice that we really could have done one other thing also. We could have just multiplied 4 times 16 so that we had log base 2 of 64. And that is 6. 2 to the 6th power is 64. But that's a little tricky if you're not familiar with your powers of 2. I mean, not everybody knows that that's 2 to the 6th power. Whereas you did know that that was 2 and that was 4. Okay. What's this equal to?
Wouldn't the natural log and the e become 1?
Uh-huh.
And it would just be the square root of 1.
This is not square root of. That's its exponent, -2. Okay? So the first thing we're going to do is take that and bring it down here, because you can do that with exponents. So this expression is equal to this. With me?
Yeah.
This is 1. So our answer is -2. Or whatever that exponent was. In other words, here's the rule. If you have any kind of log, but we'll say natural log, any kind of log, base b of b, that's always going to be equal to 1. Okay? So whatever exponent I put up there, this has to equal x, because I'm going to always be able to bring the exponent down in front to there. And since the rest of it's going to be equal to 1, it's just equal to whatever the exponent is. If I had x plus 1, it'd be equal to x plus 1. Okay? So what you look for is to see whether the base, which in this case is e, are these the same? And if they are the same, the answer is just that. a little different. What is this going to be? Log base 2 of 4 cubed.
Well, first you'd bring the exponent over, so it'd be 3 log base 2, 4.
Okay. What's this?
And then
What's that equal to again?
2.
Okay. So the answer is
6.
Okay. How about log base 5 of 125? You may not know this, but it's a good one to memorize.
It would be 3, wouldn't it?
How about log base 3, 9 to the 4th?
Uh, 8.
Good. And now they get a little trickier. Log of 1/10.
Would that be -1?
Good. Natural log of 1 over e cubed.
Would you first have to set this equal to 0, or could you just solve it like this?
No, the best way to do this is to put it like this. You see that those are the same. E to the -3 is the same as 1 over e cubed.
Oh, okay.
Okay, and once I've got it like this, what's that equal to?
-3.
Okay. Common log.
That would be...
So 3 log of 0.01. What is the log of 0.01? How else could I write that? Can I write that as 10 to some exponent?
Couldn't you do square root?
Well, there's a couple of ways to think about this. Let's analyze this all by itself. What is that? Remember, that's a base 10. And if you don't know what it is, say it's equal to x. Now translate it to exponential. So we've got 10 to the x is equal to 0.01. What does x have to be?
Would it be...
What's 10 to the -1?
1 divided by log of 10.
No, what's 10 to the -1?
1/10.
Okay, what's 10 to the -2?
100.
What's x have to be?
100.
-2. In other words, you just said it. You said 10 to the -2 is equal to 100th. That's 100th right there. So x has to be -2. Okay, so I can replace that common log of 0.01 with a -2, and now my answer is -6. We'll make sure you understand before I go on, though. See how we got all that?
Sorta.
Now let's go through it again. 10 to the 1 is 10, right?
Yes.
10 to the 2 is 100. Going the other direction, 10 to the 0 is 1. Any number to the 0 is 1. 10 to the minus 1, you said, was 1/10, which I can write like that. 10 to the minus 2 is 1/100th. So if I'm looking to solve that right there, to figure out what x has to be,
-2.
it has to be minus 2.
And then the final answer would be -6.
Right. In other words, I'm just going to replace that. We just proved that that was minus 2. 3 times minus 2 is -6. Okay. All right, these are a little interesting. We haven't done these yet. Let's do number 22. Hold on, I need to. They tell you what the log of 5 is, and they tell you what the log of 15 is. Okay? Using those two values, we have to figure out what the log of 3 is. How could I write the log of 3 using the numbers 5 and 15?
Would you just have log 15 divided by log 5?
Exactly. Okay, now what is that going to be if you expand it?
Log 15 minus log 5.
And we know what those are. They just told us to them. They told us log 5 is that number, log 15 is that number. We'll substitute it, do the subtraction. Okay?
Yep.
How can I write log of 25? In some manner where I'm going to end up using the log of 5 or the log of 15.
You could do log 15 plus log 5 plus log 5.
No. Those would have to add up. Here's what I'm going to do is I'm going to do the log of 5 squared, because 5 squared is 25. In other words, I'm going to make my 25 be 5 squared, because I know how to handle log 5. They're telling me what it is. Okay? And this, I can bring the 2 down in front, is 2 log 5. Again, substitute whatever number they gave us for log 5, 0.699. Multiply it by 2, you have your answer. So the only tricky part on these questions is how to make up the number based on the two numbers that we're dealing with. So the next one says log 75. How am I going to make my 75 out of 5 and 15?
Log 5 multiplied by log 15.
Which becomes in other words, if we're trying to get an answer and the only things we know are what the log of 5 and the log of 15 are, well, so far that hasn't done me any good. I got to separate it.
So you just do log 5 plus log 15.
Which in our case is 0.699 plus 1.17, whatever that other decimal is, 6. So whatever those two numbers are the log of 75. How about 125? How am I going to make that out of those two numbers?
To what? 125?
Uh-huh.
Log 5 cubed.
You got it. About log of 1/5.
Log 5 to the negative first power.
Okay. And now what?
Then you take the exponent over, so it'd be negative 1 log 5.
Which means it's going to be negative 0.699. Okay? And that illustrates something that's worth noting. And that's that whenever you take the log of numbers between 0 and 1, you get negative answers. In other words, this is what the log function looks like. That is y equal log of x. Okay? And this point's always going to be 1 comma 0. So if you take the log of a number greater than 1 to the right on the x-axis, you get a positive answer. If you take the log of a number x that's between 0 and 1, in other words, between those two numbers there, you get a negative answer. And the closer the x is to 0, the greater negative you get. In other words, if I were to take the log of 0.00001, I'd be at like negative a million. And in fact, as you go to 0, the log goes to negative infinity, and it never hits 0. You cannot take the log of 0, any log, common log or otherwise. It's not in its domain. Okay. About 225.
Log 15 squared.
About 28. Log of 1/15.
Log 15 to the negative 1 exponent.
And 29.
Log 15 divided by log 5 to the negative 1st power.
Okay, well, let's make sure we don't make that mistake you just made there, which is very, very easy to make. I don't think you meant what you said. What did you say? We're trying to do 29.
Or like in parentheses, log 15 divided by log 5, and then outside the parentheses to the negative 1st power.
Are you talking this? Something like that? That isn't going to work. First of all, let's be clear that this does not mean this. Okay? This is just a division of two logs. It's not the same as log of 3. This is the same as log of 3. That equals the log of 3. Okay, you with me? The difference between what I've got up here, log divided by log, is not the same as log of two numbers being divided. So I think you wanted to say this, but 1/3 is not 15 over 5. Let's just get it directly and let's make it 5 over 15. 5 over 15 is the same as 1/3. And now what does this become once I've broken it up into 5 over 15?
Log 1/3.
Right, but if we're trying to put a number on it, we did it this way because we know what the log of 5 is and we know what the log of 15 is. So how do you separate these two? Log of 5, what's the rest of it?
Minus log 15.
Okay. And then we know what that number is and we know what that number is. Okay. Let's expand some expressions. How about 30?
Log 3x.
No. Can't do that. How'd you get that? Oh, well, first of all, let's see what we're looking at here. That's the log of A times B. So, and notice that we're working in the expand expression area. So we want to use the multiplication, division, and things like that to turn this into two log expressions. In other words, that's equal to the log base 2 of 9 plus the log base 2 of x. Would you want to know?
What?
Do you see how I got that?
Yeah.
Okay. Now, as far as what the log base 2 of 9 is, well, if I wanted to get that number out of a calculator, and it doesn't look like they want you to come up with numbers here. It looks like this is going to be our answer, okay? Because the log base 2 of 9 is not 3. 2 cubed is not 9. So it's slightly more than 3, which means it's not an integer, which means we're not going to be able to come up with this answer without going into a calculator. And if we tried to get this number out of a calculator, we would have to use the change of base formula, which turns it into what? What does log base 2 of 9 turn into? If I truly had to get it out of my calculator, I'd have to use the change of base.
It would be a decimal.
Well, it would be the log of 9 divided by the log of 2. In other words, it's always the log of the upper number divided by the log of the base. Okay, this number I can get out of a calculator. In other words, my calculator has an LOG key. And this happens, I can make this common log, or I can even make it natural log. That relationship is the same. Common log of 9 divided by log of 2 is the same as natural log of 9 divided by natural log of 2. So when you go to convert odd bases, and when I say odd, I mean anything that's not 10 or E is considered an odd base to me, because it's not commonly used. You have to convert it. Whether they wanted you to do that part or not, I don't know. This might have been an acceptable answer, but I actually prefer log. No, this is an acceptable answer, actually. All right, how about 31? Natural log of 22x.
You would raise it to the e, so natural log e becomes 1.
Okay, use just the multiplication rule. Remember what we're doing here is we're merely expanding these.
Oh, okay.
We're not trying to come up with a number.
22 plus natural log x.
That's all they want you to do. Okay, how about this one?
Natural log 4 plus 5 log x.
Almost. The 5 actually, oh, you're absolutely right. You said log 4 plus 5 log x. Perfect, actually. And 36?
Log base 6, 10, minus log base 6 minus, or 3, just 3.
Number 33, is that 33, not 36? This one here.
6 log base 6x.
Okay. I wondered where you were getting those numbers, and then I saw this one down here. Was that the one you were doing, 36?
Yeah.
Okay. How about 34?
Log base 4, 4 minus log base 4, 3.
And one of those can easily be reduced, simplified more. In other words,
The first one would just become more.
yeah, whenever you come across a log that you can figure out without a calculator, in other words, it turns into an integer, you should do so. So this fully expands to this. Okay, 35.
Is that already simplified?
Well, it sure seems to me it is. I'm guessing that when they say expand the expression, they must mean that when you have this, you should use the change of base. So let's go ahead and use the change of base on some of these.
It would be log 25 divided by log 3.
Yeah, okay, as long as you know that. I mean, that's not something we have to repeat over and over. How about this one? Don't change your base. Yeah, go ahead.
Log base 6, 10 minus log base 6, 3.
Correct. Be careful not to divide it, yeah. And 37, can you just barely read? That says natural log of 3 times x times y cubed.
Natural log 3 plus natural log x plus 3 natural log y.
Good. And let me jump around here. I don't think you need all these. Let's do 39.
Okay. Log base 8 2 plus 2 log x.
Oh, what'd you say? Log base 8, what'd you do with the 64?
Couldn't that just become 2?
Well, first of all, let's write it out. In other words, there's the log of 64. Plus, now it's 2 log of x, right? In other words, I don't know if you jumped a couple steps all at once or not, but if we take this step by step, this is my next line, correct?
Yeah.
This is the number 2.
Yeah. I just did that all at once.
Ah, okay. Okay. Which is fine. I know you know how to do 40. How about 41?
5, 6 log base 3, 12 plus 9 log base 3x.
Good. How about this one? 42. Radical sign.
Wouldn't that be half log x?
Good. How about this one?
Log 3 plus natural log, no, it's log 3 plus 4 log y minus 3 natural log x.
Good. Very good. About 44.
1/4 log, or no, it would be 3/4 log x.
Very good. And 45.
Half log 4 plus half log x.
Okay, we can simplify that. Let me write, hold on, let me find my cursor here. So, what'd you say? You said half log base 2 of 4 plus half.
Would the first part just become 1?
Well, yeah, that is 2 times a half, so that becomes 1. And that's all. In other words, the rest of the answer is going to be this. Okay? All right. You're pretty good at this. Let's move on. We don't have much more logs to do, but we do have log equations. And we've done a little bit of log equations. I can't remember. Well, first of all, there's a couple of exponential equations that you should know how to do. Something like this. And I can't remember if we've talked about these or not. Let's just review them. Can you solve that without using logs?
Yeah. You would do the left half would be 2, and then the exponents would be 6x.
Okay, let's do it one step at a time. First step is to represent the 4 as 2 squared. In other words, that's the same thing as the top line. Over here, I'm going to represent the 8 as 2 cubed, and I always use parentheses. Those parentheses are vital, incidentally. If I didn't have the parentheses, this would have a different meaning. Now, using the rules of exponents, the left side becomes 2 to the 6x. Like you said, what's the right side become?
2 to the 3x plus 3.
And now what can I do?
You can take out the bases, so it's just 6x equals 3x plus 3.
Correct.
And then the answer would be x equals 1.
Got it. Good. Solve this. And you do need to use logs here.
It would be log base 2, 7 equals x.
Almost. Let's just go through this process because I think terminology is important here. You're going to take the logs of both sides of this equation, correct? That's how you're going to solve it?
Yeah.
What kind of log? What base log?
Log base 10, right?
We can do that. I thought
could you use
originally you could use 2, and there is an advantage in using 2. Let's check out both methods. Let's just use 2, okay? However, I can't take the log base 2 of the left and the log base 7 of the right. I'm not allowed to do that. Whatever I do to the left, I have to do precisely the same to the right. So I got to take log base 2 on the right also. Now, what does the left become?
It just becomes x.
So there's my answer. One step, okay? So there was an advantage in doing one step. The problem is that I can't get that number out of a calculator. Use change of base. What's that equal to?
Log 7 divided by log 2.
Okay. Now let's go back and do it. That's a total of 2 steps. But now, instead of taking log base 2, let's take common log. Okay? So now I'm taking log base 10. What's the next step?
It would be x log 2.
There's my first step.
And then it would just become 2x, correct? And then
Now, hold on. How do you solve for x here? Remember, that's just a number.
It would become 2x, right?
No. This is not 2. That's the log base 10 of 2. Which means 10 to some exponent equals 2. Well, what is that number? Somewhere between 1 and 2. It's like 1.1 or something. Okay? But the thing is that does not convert into a number. That's a number you can only get off your calculator. The answer has to be, I'm going to divide both sides by log of 2. Now, log of 2 divided by log of 2, I don't care what that number is, it becomes x. So, two steps again. The first step, the second step, to get to the same answer. That's what we got when we did it the other way. So, taking the log base 2 of this isn't all that beneficial. It seems like it is because it immediately gets to x. But what I've kind of found is that, boy, if you just stick with natural log everywhere, you're going to be better off. And there's a reason you want to get used to natural log, because when you get into pre-calc and calc, it's all natural log, pretty much. It's 95% natural log. You don't even hear of other logs. Natural log is absolutely critical to calculus. Okay, so when I run up against a problem like this, where I'm trying to solve it for a variable that's in the exponent, I'm telling myself I'm going to take the natural log of both sides every time. Okay, then I'm going to bring the x down, so I get x natural log of 2 equals natural log of 7, and I'm going to divide both sides by natural log of 2, and I get natural log of 7 divided by natural log of 2. Now remember I said that that's the same as the common log of 7 divided by the common log of 2. So our answers were the same. They just looked a little different. Okay? So rather than trying to figure out what special log you should take to solve these equations, I would suggest just always take natural log or common log. The advantage of taking either one is you can get your answer immediately on the calculator. You don't have to go through the change of base. All right, let's solve a log equation. First step.
Subtract 4 from both sides. Add a log base 10 to both sides as well.
Yeah, this might be the one case where I would take the common log of both sides. Because first of all, I'm going to be able to deal with the common log of 17 and the common log of numbers that are 10 or multiples of 10, or rather powers of 10, are real easy. So I'm going to take just that. And if it's common log, I don't need to write 10. If you write log with no base at all, it means base 10. Okay? So what's the left become?
2x minus 3.
Keep going.
You add 3 to both sides, and then you divide it by 2.
Okay, so 2x equals log 17, which is just a number. And divide that by 2, and divide that by 2, and you solve for x. And that's a perfectly acceptable format for the answer, incidentally. Just because this is a number and this is a number doesn't mean you have to add them together. Because when you add these together and try to represent it as a decimal, it's at best an approximation. If I want a precise answer, this is it. I could change the 3/2 to 1.5, but that's not important. The question is, what do you do when you have the log of some number plus another number, and you leave it that way? It's a little bit like if you have an answer square root of 3 plus 2. You don't do anything with that. That's the official answer right there. Okay, here we go. Getting harder. This was derived from Newton's law of cooling, where the temperature of something comes down to this equation. In other words, how do we solve this equation? This is solving an exponential equation. Why is it an exponential equation? Tell me.
Because of the variables?
Because the only variable, this isn't a variable, that's the number e, okay? The only variable is t, and it's in the exponent. That's what makes it an exponential equation, and that's all. In other words, if I say 100 equals t cubed, that's an algebraic expression, not an exponential one. It's only when your variable is in the exponent that you're going to have to use logs to solve it. And usually that's the only way to solve it. So let's break this thing down. Let's see if we can isolate that and then deal with it the way we've been dealing with all these problems. By taking some log of both sides. But first of all, we have to isolate that. What can we do to isolate that?
To isolate the exponent?
No, to isolate this. Once we can isolate that, and then I'll show you how we're going to solve it. But first of all, let's isolate it.
Subtract 70 by both sides.
Okay, and then what?
Divide both sides by 142.
So we got 30 divided by 142 equals e to the minus 0.046t. T is in number of days or hours. It can be in anything, but it's some time frame. Actually, in this particular problem, I believe t is in minutes. It is. Okay? So, how do I solve for t? E to some exponent is equal to this number. And that's what the essence of what we have to solve for. And there's tons and tons of real life problems that are like this, where they're your variables in the exponent. So without logs, we would have no way to do this. But with logs, it's pretty easy. I can take the natural log, and here I'm definitely going to use the natural log. Okay. So this becomes that exponent. Because first of all, I'm going to bring that exponent down in front, and then I'm going to turn natural log of e into 1. So I get this equals natural log of 30 over 142. I'm just going to leave it like that for the moment. I don't need to do anything with it. Now what? What's t equal to?
Wouldn't you first have to divide everything by negative 0.046?
We have to divide both sides by negative 0.046. In other words, as long as I divide this by whatever its coefficient is, I'm going to end up with t. Okay? Since I divided that side, I have to divide that side. So that's what t is equal to. Now, can you simplify that? Let me put the t on the other side. Hold on. T is equal to this whole thing, but it's a little complicated. It's a little strange looking.
Could you just change the top part to natural log 30 minus natural log 142?
Now, what do I do with the denominator?
Would you just keep it the same? Or couldn't you bring it to the top and start to get rid of the negative?
No, can't do that. We're not talking negative exponents. If it was a negative exponent, yes, you could do that. Turn it positive and put it in the numerator. No, what this means is I'm dividing whatever my numerator is by this number. Well, that's my numerator. So I have to divide both terms by that number, by that denominator. Okay? So this is going to produce a number. Now, notice that has to be positive because you're taking the natural log of a number greater than 1. This has to be positive, which means I have a negative number minus a negative number. I'm going to end up with a positive number because this is going to be bigger than the natural log of 30. So I'm going to end up with a positive number, which is good. You don't want to end up with a t that's negative. Time can never be negative. So it's just a little check. You can get each of these numbers out of a calculator. In other words, I can put that in, and come up with a precise number for t if I'm trying to solve for t. Okay. The other thing I could do here is I could convert this to a decimal instead and just say the natural log of that decimal divided by this number. That would also be acceptable. Let's see, don't let me run over here. What can we do in 5 minutes? All right, here's another one. This is pretty straightforward, actually.
You could divide both sides by log base 3.
Yeah, I mean, it's okay to look at it like that, and that gets the job done. You end up with the right answer, 5x minus 1 equals x plus 7. But you're not really doing that. You're not really dividing both sides by log base 3. However, it's certainly correct to say that if the log base 3 of one entity equals the log base 3 of a second entity, then you can equate the entities. It's okay to do this. In the same way that if I said e to the 3x equals e to the 2x plus 2, I'm not really dividing by e. I'm just saying, well, it's okay to equate exponents. They have to be the same. And this could be any number. It could be 2. It doesn't have to be e. If you have one base to an exponent equals the same base to a different exponent, you can equate the exponents. And you're not really doing division. Well, in that same sense, you're not really dividing by log base 3. It's okay to look at that way, though. That's not harmful. So this, when you're solving a log equation, almost always you have to convert it to exponential format. That's the way to solve it.
It would be 3x plus 1 equals 5 to the second power. Should just be 25. Or x equals 8.
Good. And finally, let's end on this one here, because this next one illustrates the problems with logs. Now, we're going to end up having to use an exponential representation here. but we can't represent this thing exponentially until we get one log function, not two.
So it would first become log 5x multiplied by x minus 1. But then you could just have that x divided by 1. Come in here.
No, that's the very first step. You have to do that. Now I have a single expression. Well, I can certainly do that multiplication. Let's do that multiplication. That's 5x squared minus 5x. That's equal to 2. Now is where you turn it into an exponential expression. In other words, once you've got the log of some argument, this being the argument, equals some number, now you're ready to solve it by turning it into an exponential expression. What's the exponential expression?
5x squared minus 5x equals 2, or 10 to the second power.
So 5x squared minus 5x equals 100. That's 10 to the second power. What next?
Would you subtract 100 from both sides?
Okay.
Then divide the whole thing by 5.
Yeah, okay. Which gives me x squared minus x minus 20 equals 0. That's where
And then it would just be x minus 5 in parentheses and x plus 4. So the answer would be positive 5 and negative 4, but then you can't have a negative, so it'd just be positive 5.
You can't necessarily not work with a negative x. It depends on what the original thing looks like. In other words, I might be able to work with a negative x if I had x plus 3. If this said x plus 3, I could work with a small negative x. I couldn't handle negative 4, but you're correct. When we check both of our answers, the negative 4 violates both of these domains. All it has to do is violate one of them. In other words, if it violates that one or that one, we can't use it. We have to throw it out. And that negative 4 violates both of them. I think I may have done this one for you the last time. Anyway, I'll take another picture of practice problems at the end of this chapter, and I will email them to you after your brother's session. And you can do that for homework this week, if you like.
All right.
Okay? I will talk to you next Friday. Liza, have a good week.
You too.